Today, industrial facilities generally include a great variety of machines found in different locations, all of which work towards achieving the same purpose. Increasingly powerful control devices have been developed in order to deal with the growing complexity of equipments. Hundreds or even thousands of kilometers of cables run throughout the plant in every direction. Each sensor or actuator needs at least one cable in order to communicate with control devices. Controlling and monitoring such equipment require a large number of devices to observe, measure, detect, and act while updating information. The control devices have an increasingly greater appetite for data, which has to be delivered. This abundance of equipment and wires lends to complex wiring diagrams and laborious management and coordination of tasks. Even simple maintenance can become a delicate and tedious operation. In most cases, this technical situation creates an obstacle to further development and expansion. But what if a single cable were able to transmit all of this information? Électricité de France took up this challenge by co-founding the FIP Club in June 1986. The FIP Club is an association of users and manufacturers whose purpose is to define, standardize, and promote the FIP concept. As soon as the first components of FIP were available, the Studies and Research Department of Électricité de France began experiments in their Château laboratories. FIP stands for Factory Instrumentation Protocol. It is a field bus designed to connect sensors, actuators, and control devices in an industrial environment. To further experiment, it was necessary to test it in real industrial conditions. Convinced by the initial results, the Hydroelectric Production Department recommended that the first FIP industrial prototype would be installed at the Revin power plant. The objectives of this experiment were to use the results of fault recorder in order to analyze defects and to edit the logbook by means of an information control device. FIP and Revin share a common philosophy based on this simple concept: start out with an elementary function in order to achieve powerful services. The Revin power plant, situated in the Ardennes in northern France, is an energy transfer station which operates by water pumping. A first conventional reservoir stocks water from an affluent of the Meuse. 4 intake tunnels measuring 6 meters in diameter carry this water to 4 turbopump sets, each with a power of 200 megawatts. During the pumping phase, they propel the water into an upper basin located on a hill 230 meters above. It has a usable capacity of 7 million cubic meters. At any time, the Interregional Center for Energy Movement in Nancy can tap this energy by simple remote control. The valves open, The falling water causes the turbines to rotate. They, in turn, activate the generator. In 2 minutes, Revin's 800 megawatts are available with an output of 400,000 volts, which can either help regulate the entire network or make up for mechanical failure in another major power station. Because the different organs of the Revin plant are so spread out, a field bus measuring 1,000 meters was needed. The same functions carried out by traditional means would have required 200 kilometers of cables. The cable consists of a simple shielded twisted pair. It begins in the control room where FIP also receives orders from the center in Nancy and the level of the upper basin. It goes through a 63 kilovolt substation. Crosses the 300 meters from the access gallery to the underground plant. Services the control devices in the 4 turbopump sets. Goes up the wiring shaft containing 13,000 volts rods to the 400,000 volt transformer station, which it crosses before following the hill back down to the draining room of the lower basin. Information is gathered in the cabinets built next to the control device sets. These cabinets were built in collaboration with CGEE-Alsthom. They include acquisition boards, which gather the measurements and convert them into data. A FIP communication board reads this information and forwards it through a coupling box every 20 milliseconds to the entire FIP network. A microcomputer, situated in the control room, detects the events and records them in the operation logbook periodically by 1 day, 1 week, 1 month, and even 1 year. Simultaneously, at each maneuver, the microcomputer records any changes in the state of the turbopump sets. In the case of an unforeseen incident, and on simple request by the on-duty personnel, FIP is able to give a rapid analysis and diagnosis of the defect. The situation can thus be dealt with effectively. But what actually goes on inside this field bus? Here's a section of FIP which consists of a process controller, a fault monitor, an actuator, and 2 sensors. Periodically, the arbitrator, which controls access to the network, transmits a request for information to the field bus. Sensor A acknowledges that it holds this information and gets ready to broadcast it. The fault monitor and process controller pick up this measure. The information is sent by Sensor A throughout the whole FIP network, but only those stations concerned pick it up. The bus arbitrator then prepares the network for another operation. This process is repeated 5,000 times per second. Until now, the field bus was the missing link in the architecture of industrial sites. FIP is a precursor. It is a field bus which has been designed to benefit from the full processing power of future smart sensors and actuators. Tomorrow, FIP sensors, whose prototypes already exist, will be connected directly to the FIP cable. Électricité de France, within the framework of the CIAME, is involved in determining the specifications of these future smart sensors and actuators. FIP is now an industrial reality. It is operating in an advanced technology hydroelectric power plant. FIP has brought together the giant world of machines and the microcosm of computer chips.